Sorry for the jacket, I'm from San Diego. I'll explain the title first. I'll explain what I mean by very fast, don't worry. I'm mostly going to talk about the sources and the detectors, but let me briefly introduce what my research group does. We develop silicon photonics and 2.5D or 3D silicon photonics in some cases for quantum optics. Mainly we've been looking at entangled photon pair generation along with filters on the chip and couplers and these little elemental building blocks. We've always been looking at modulators, detectors. But also we have been exploring indium phosphide on silicon lasers with collaborators, lithium niobate on silicon modulators. You'll see some examples, and this is done through a bonding process. We've been participating in multi-project wafers for the last 10 years now, with big companies, with government labs as well, and I'll be happy to share our experiences on that. You'll see examples. Pretty much everything you see here was done through a foundry fabrication and sometimes by modifying either the device or the process to sort of reach the point where you wouldn't ask how the device was made. You just look at the performance and say if it was acceptable or not. We're not quite there yet, but let's start with the very fast. The reason for picking very fast is Professor Andy Wiener is going to give a talk, presumably on ultra-fast, and that word is already in wide use, and that means something specific. It means femtosecond pulses and basic physics. What I'm trying to describe is just not that fast, but pretty fast, and pretty fast doesn't make sense. We are talking about sources in which we want to speed up what are called trials. Explain that. Basically, it's how quickly you can run an experiment. If you're trying to do quantum sampling, or you're basically trying to do QKD, the faster you can use the channel, the faster you can get your data across. So we're trying to speed that up. And I think integrated photonics plays a role here. And for detectors, it's quite obvious we're trying to detect waveforms at very low optical powers, basically build a sampling oscilloscope. So to explain what I mean by trial, almost everyone here knows this, but for the students, basically a trial is often called channel use. So if you come from a communications background for a discrete time channel, here's the capacity, the Shayan capacity, and that, if you read the units carefully, is bits per channel use. What does that mean? Well, most of the time, we just say that there's one channel use or one experiment is run in a certain amount of time, microsecond or nanosecond, and so the channel capacity is in bits per second. But if this is a variable and you can speed things up, then CBPS can increase even if you're not really changing the fundamental physics of this. And we're seeing that integrated photonics quite easily over tabletop optics improves this rate of channel use by a factor of 100 or 1,000. In addition to the parallelism, you can get 100 or 1,000 different devices on a chip. Now we have 4 to 5 orders of magnitude improvement, rather than just 2. So we'll see some examples of what I mean by this, or just to be a little bit more specific in QKD or for transceivers. For instance, in QKD, Alice and Bob are going bit by bit, and they're rotating the polarization settings. If you can do that 100 or 1,000 times faster using integrated photonics, you can certainly communicate faster. And similarly, if you're trying to do this probabilistic thing of entanglement swapping, if you can do each trial faster, in addition to going parallel, you would certainly improve. And this is certainly something where I think our version of integrated photonics, fast modulators, fast lasers can help. You can go a little bit deeper. I won't spend time on this, but even if you look at these graphs that predict or give the rationale for why we need quantum repeaters, the axis here, the argument that's being made is the time to distribute a single entangled photon pair, and this was generated with an assumption of 10 gigahertz repetition rates. And not many of us today use equipment in our lab with 10 gigahertz repetition rates. And so certainly this is something which I would call is low-hanging fruit for integrated optics. This goes back more than 50 years. If you go back to Loisel's textbook, the differential noise of an SPDC process, this variance goes to 0, but you have to calculate this variance over a time window. And the faster you can do this, the faster you can use this for sensors or entanglement, right? And so the way to do this is basically make small, efficient cavities. And that's where we come in. The technology of integrated photonics, especially as used in AIM and elsewhere, is ideal for small cavities and highly nonlinear devices. So, I've shown this view graph before. Photon generation and entanglement creation apparatus has been going through a rapid miniaturization from room-sized apparatus to breadboard-sized, and obviously we're all here to talk about microchips. But what that also means is as the size shrinks in parallel, and we are arguing that they are linked, the trial rates, or how often you can run the experiments, have gone from kilohertz repetition rates for these lasers to things on a chip that can go, as we'll see, way beyond gigahertz. And in some cases, you don't even need mode-lock lasers because the power requirement also comes down. It seems to be a win-win in many different ways. So what do we need to speed up these trials to the 10 to 100 gigahertz per attempt regime? First of all, we need small devices because, as we see from Loisel's papers and many others, you need a photon lifetime that's compatible with 10 to 100 gigahertz. And what that means is basically microring resonators with a Q of about 100,000, for instance. And it's a different regime from the ultra-high Q physics applications, which are typically on the nanosecond scale. But for this, it means that you have to be able to process those bandwidths as well. So ultra-high bandwidth, which we're looking for from our detectors and modulators, goes hand in hand with these cavities, these microring resonators that have a photon lifetime of a little bit less than 100 picoseconds. But if you have a small device, then it had better work well, which means it has to be intrinsically nonlinear, and the phase matching has to be done very well. So, long story short, today we have silicon microring resonators that have a pair generation rate of about 150 megahertz per milliwatt squared. It's very tempting to say, I'm going to put 3 milliwatts in there and get a gigahertz of photon, which would, we'd all run out in the streets. But that's not happening, at least not yet. We are working very hard to keep the Qs high at higher pump powers. But today, we run them at about 1/10 of a milliwatt. Maybe you'd be lucky to push it to a milliwatt. So we can get 10 megahertz, 20 megahertz of pair generation rates on a chip per device. Okay? But this also means, of course, as I just said, that we have to use 100 gigahertz of bandwidths. So modulators really have to speed up, and detectors have to speed up. And I think you have to be able to process frequency very well. And this means that on a chip, we have to be able to do this kind of stuff in a way that we can generate the pump pulses without spending $1 million per chip. Because if you're spending $1 million, you can buy a table. And operating the source that is scalable, manufacturable, parallelizable, and low cost. And this leads to iterations of microchips that we have designed and we continue to design on various different processes, taking a multi-project wafer and customizing it in our lab, back-end processing, front-end, begging foundries, pleading with foundries. We haven't tried blackmailing yet. That's next. In 2012, many of you have seen our work from back then when we used microring resonators. Back then, it was a coupled microring device. We were studying heralded single photons from a silicon photonic chip. Since then, we have gone on to show wavelength division multiplexing. We have been able to control the degree of entanglement by programming the coupling between the microresonators. We have proved that there is, I think we're out of battery on this one. We've been able to prove, let's see, is there a pointer on this? Yeah, there's a pointer here. Entanglement, time energy entanglement, Franzen interferometry, how to stabilize the temperature. These are incremental steps. I'll show you one or two cool results from this, in my opinion. One was you can design a microring that simultaneously generates entanglement at 1310 and at 1550 in parallel. And so it's a six-fold resonance. The Qs are quite high. The pump power requirements are about 0.1 milliwatts, and the pair generation rates were not optimal, but there are a few megahertz. And the cars in there several hundred. The visibilities were pretty good, but I think not world record results. And recently, Karthik Srinivasan's group has designed a microring that can actually generate both at telecom and visible. So the engineering of microring resonators is continuously improving. Ours was a foundry process. Karthik's is an e-beam process, and somewhere they're going to work together. We love the idea of pair generation without mode lock lasers. And what that means is, well, I'm going to take a CW laser diode and an electro-optic modulator. And for the RF waveforms, I'm going to take a sine wave and a nonlinear diode called a step recovery diode or a snap recovery diode. So now we have two inexpensive CW oscillators. The parameters of the SRG are matched to the photon lifetime in the cavity. So the photon lifetime of this cavity is about 70 picoseconds. This, when driven by a sine wave at 1 gigahertz, generates 70 picosecond pulses after the electro-optic modulator. And so in this case, we have essentially a few dollars worth of components and hopefully an inexpensive chip. There's a PN diode that's monitoring whether the light is on resonance. We use that to lock the microring onto the wavelength. And so this is a pretty easy way of at least getting a small, compact, inexpensive pair source. And the repetition rate was about 1 gigahertz, and we have pushed that to a few gigahertz. With about last year, we were interested in getting the laser onto the same platform as the pair generation. And this is some work in which this is a hybrid laser made by Intel. It needs about 100 milliamps of current and about 1 volt. It's their production process. And the microrings here were on a separate silicon photonic chip for a number of different reasons. But it's the same technology as goes on their silicon photonics process. It's not it's not fully integrated yet, but an unstabilized, unpackaged. It's not an external cavity laser. It's a fully integrated hybrid silicon photonic laser. Gives you enough narrow line width and enough stability and polarization stability and quality to give you a car of several hundred and a G2s of fairly good numbers. The heralding efficiency is not very good, but that's our fault for not designing the microwave very well. So hybrid lasers, as are out there in industry right now, are compatible with silicon photonic microwings for pair generation. And there are more details in these two. This was done at 1310 nanometers. There could be work at 1550, but I think most of the hybrid lasers are at 1310 right now. For where microwings are, this is about a year old now. Some of the results may have changed, but you can look up our paper in Optics Express. We were pushing whether the overall CAR numbers and G2 numbers for silicon photonics could compete with lithium niobate, which is, after all, the gold standard, or PPKTP. And we were able to push CARs to about 12,000, or even at the highest pump powers, we're generating 5 or 6 megahertz. CARs are about 500 or 600. The generation rate, as you can read here, is about 150 megahertz per milliwatt squared. The line widths are on the order of a gigahertz, so you have to do WDM within that. And this, basically by engineering the microring and the coupling and reducing the losses and reflow of the waveguides and a lot of different things, went into the technology of this. Long story short, the numbers look pretty good. And so I think we can actually claim silicon photonics does work as a pair source technology. Well, then the question comes, work for what? And so one of the things we did more recently is to sort of throw away the laser and say, in the internet, you have lots of data streams going around between Alice's and Bob's, their computers. So could we just use some excess light from the laser, from the internet itself? So Alice and Bob are two 10 gigabit per second NRZ communication computers, classical NIC cards. And we take some light from that channel. It turns out at 10 gigabits per second NRZ, the pulse width is very well matched to some of our microring resonators. And the pump powers are in the order of, well, that's 1 milliwatt. If I take a fraction of that, that's exactly what I needed. The fact that an NRZ data stream is random is irrelevant because pair generation itself is random. And so we have a random pump pumping a random process, and therefore you get pair generation using a fraction of 10 gigabit per second NRZ data streams. So if you have two sort of computers in a network that you can borrow briefly, you can generate enough photon pairs here to perhaps exchange a key or something, and the quality is quite good. Generated this way, we can get cars of over 1,000 or even more than 100 at the highest pump powers. And generated this way, using a transceiver bought off the internet, we can get G2s that are approaching 0.02. And so this is quite exciting, right? I mean, not only can we bring the laser onto the wafer, maybe we don't need that at all. Maybe we can just buy our lasers off the internet. So we'll see which way we adopt going forward. But certainly integration for its own sake may compete against other ideas too. So then we tried to do this and actually send some data from Alice to Bob, who are at least this far apart. What that means is we took this photon pair generation stream that are pumped off this 10G data stream, and we send them through a little short, long encoder. Randomly select either the photons go through the long path or the short path. This is the time difference between the photons encoding a certain message. And what this graph shows is that the histogram is basically preserved even after a fairly large number of bits. So things don't drift. Neither the transceiver drifts nor the setup drifts. And of course, one easy thing and one nice thing to do would be to integrate all of this onto a platform. And I think we can. These are modulators, switches, delay lines, etc. And so what this does is basically Alice can send a key, and Bob can receive the key and do the XOR. We did not do a basis change, so this is not technically QKD. It is close to QKD. But we were able to send a message, and this graininess is the error rate, which is a few percent. So the error rates are comparable to what you would see in a tabletop QKD experiment using time and entanglement. But the pump here was a 10 gigabit per second data stream. And we can even scale this further to a 40 gig data stream or something. Okay, so the source side is getting interesting. We have good performance, cars over 10,000 if you need them, lots of microrings. Our biggest chips have about 100 microrings on them. They can all be pumped simultaneously. It's a monitoring nightmare. But at the same time, we want to push the detector side. And so I'm going to, switch gears here a little bit and tell you about something I hope all of us are familiar with, which is an optical sampling oscilloscope. So that's an optical sampling oscilloscope. We have them in our labs, and it's a basic thing for testing modulators, so on and so forth. But the problem is this thing, well, it's expensive, but the minimum detectable power is on the order of, let's say, 10 microwatts or so. So if you're testing high-speed modulators on wafer scale, and you haven't invested time and effort into packaging each single device, that's a problem. Right? You'd like to be able to get this kind of performance at very low power levels. And in essence, that's what we did. So this is a trace of a signal measured using a normal oscilloscope. And this is what we'll call our SNSPD, or nanowire single photon detector oscilloscope. It's the same waveform, but if you look at the numbers, this goes between -8 and -14 dBm. This goes between -112 and -118 dBm. So there's a 100 dB difference in received power level. But if you zoom in and look at the traces, they're reproduced almost exactly. So what's going on? Well, the idea is not new. I think many of you have probably tried this in your labs. How it works is a start-stop measurement. So you have a clock. This is an electronic clock signal. And in every clock, you pick out one photon from your waveform to measure. And you time tag the difference between this photon that you measure and the clock. So that is a particular delta t. You increment the histogram. In the next clock, here's another delta t. You increment a different histogram. And in the next clock, you have a different delta t, and you increment the histogram, and so on. And if you keep doing this, the histogram becomes the waveform that you're trying to measure. More precisely, it's a sampled version of the waveform, but that's okay, because the way we generate signals are sampled anyway. And if you have enough resolution here, that's not a problem. So people have been doing this for a while, time-correlated single photon counting. That's what it does. We've just used it as an oscilloscope. But the point is, we've used a pretty nice modulator, we've used a pretty nice detector, and a pretty nice card to be able to measure signals that any arbitrary waveform generator can generate at less than 100 femtowatts of received power. More details offline, and we are still working. This is pre-publication, just to get you guys excited. But here are eye diagrams measured at -100 dBm optical power at the received front end. That's at 40 gigahertz, that's at 90 gigahertz, and that's at 102 gigahertz. And the length to resolution ratio is about 4,000. And so here the measurement time, it's a sampling scope. It builds up over time, but the time is only about 2 minutes. And to measure a signal, to identify the frequency, it takes about 150 milliseconds. And so we could identify these signals way below 5 orders of magnitude below the single quantum limit. And so it's an interesting way of building oscilloscopes. And it shows what you can do with state-of-the-art integrated photonic components such as modulators and SNSPDs, and also electronics. So 3 things working together here. So, I mean, integrated photonics basically can really change the parameters not only of how fast you do your experiments, but also what kind of performance you get, but how do universities play a role in this? So let me present a case study from my previous experience here. I was fortunate to be part of an NSF center on integrated access networks. This is now concluded, but is continuing at the University of Arizona, which is the headquarters of this. And one of the projects here was a multi-project wafer in which a bunch of us collaborated to share the space on a multi-project wafer run. But it was under a research umbrella. It was under a research team. So there was some coordination into what we wanted. They were all intended for similar purposes to be used in access networks, integrated access networks. And so when we requested process modifications, it was sort of common across all of us. And so we really benefited from that level of collaboration as opposed to a full open MPW. And so what that allowed us to do, this multi-year ERC-like program, is to go through iterations of the chip in which they're not just single components, but even version 1 had some level of integration. And version 2, once we saw that worked and what didn't work, enabled us to be more bold and adventurous and actually improve performance. And there were lots of little details in this. For instance, these bends are not constant radius bends, and they're not constant width bends. They're adiabatically widened bends so that we can get a heater in there, and a fast heater. These directional couplers are weird asymmetric directional couplers that Sandia had proposed. We worked with them, we revised them, and then we measured the couplers. These are quite flat over more than 60 nanometers, and then we used them in several places. And we got iterations through that allowed even a group of universities to do this. We had a VOA, a variable optical attenuator, that worked. It gave us 15 dB the first time. The next time, we were a bit more adventurous, and for the same amount of current, we got 35 dB. Right? And so long story short, the eye diagrams that began at about 9 dB ended up going, well, this may not seem a lot to a physicist, but from a systems perspective, that was quite a lot. And so this was the power of a few universities working together under a center program, and I hope that something like this could be architected for our future programs here. And so we got some nice papers in which the CS argument of, look, we have drawers and shelves full of this stuff could be replaced by chips. There was a live demo for this, and it was really a very nice project. There were many positive outcomes of working in this way. We started a collaboration between universities and a research lab that still continues 7 years later, and we have included them in other programs as well. And the graduate students and postdocs, many of them, this was their first exposure to photonics TCAD. It's not so common 7 or 8 years ago. And so many of them were snapped up by companies even before they got their PhD, or right after, and there were some companies that were started out of the universities. In fact, I can think of 3 from UCST itself. So this was very exciting, and some new international collaborations came out of this. And there's a lot to look forward to in this gray zone between a full open MPW, or here's the process, take it or leave it, and the kind of resources that we have at universities in-house. I'll leave it here and take some questions. We have been fortunate to receive support from a large number of agencies as well as companies. We have run processes with a number of these people, and we continue to do that. We look forward to working with AIM Photonics and with any other research groups that we can help. This is San Diego, so do come and visit us. And I think this is winter, but it makes no difference. But we'll see you at the Optical Fiber Conference, if not sooner. Thanks very much. Yes, Mo. Yes.
Could you just wait for a second? The microphone is coming.
I think Professor Boyd was right. There is a dead spot here.
Thank you. So on the sampling oscilloscope,
yeah,
great results. I was wondering, what's the speed of SNSPD by itself that you use for these experiments? That you got 40 giga and 100 gigasample?
Well, the key here is not so much the speed of the SNSPD, but how low you can get the jitter,
Okay.
because it's a histogram that builds up over time. And so to get these kinds of results, you can roughly divide 1 over that. And so that gives you an estimate that the timing jitter is down in the single-digit picoseconds. And similarly, the RF waveform has to be imprinted onto an optical carrier. So the bandwidth of that modulator has to be on the order of beyond 100 gigahertz. And I believe a modulator, this is a hybrid silicon photonic modulator with about 200 gigahertz of 3 dB bandwidth. Again, one of those lithium niobate on silicon things that is sort of taking the world by storm. But also the SNSPDs, these were built by Carl Berggren's group at MIT, and it's a collaboration, Matt Shaw's group at JPL, Wolfgang Becker of Becker and Hickel. This is a pretty state-of-the-art card, and this is our modulator. So it's sort of best in class of each of these three working together. It was quite an experiment. The student who did this is pretty fantastic. Yeah.
No other questions? Let's thank Dr. Shayan Mookherjea. Mookherjea, sorry.
Mookherjea.